So we're going to start on the second session proper. We're running about 17 minutes behind schedule, but that's all okay. It might be that more of the final demonstration, more of the final discussion at the end happens in the pub rather than in this lecture theatre. But anyway, so it's my great pleasure to welcome Roy Patterson here to talk about the auditory imaging model, in particular the development of the auditory imaging software, and a bit of history from here as a very long-running project. So, Roy, over to you.
So this is the auditory image software package. I'm going to tell you about the early stages when we tried to do this thing without all the tools you have now, and how we learned some of the lessons that I suspect many of you know a lot about now. So this is the version that appeared in 1992. So the purpose of this model is to simulate the signal processing performed by the auditory system as it transforms a sound into your first impression of a sound. If something makes a sound, we need a better sound, and you don't see the source, your ears automatically make an image of what's coming in. You don't have any earlids the way you have eyelids, because sound is hearing is your warning sound, warning sense. And I want to just illustrate the construction of the auditory image so that you know what the software did, and then I'll tell you a little about the project management of issues that I think remain relevant today. In fact, from this morning's talk, I know they are. Okay, so the technology we had just managed to get in the late 80s, we got workstations, sun stations, deck stations with 21-inch screens. We were the height of modernity. We had Unix, we had T-Shell, which made life a lot better, and we had X11 for our Windows. We were using Emacs, C, and SCCS, Source Code Control System, which was the Unix version of the day, which I'll just say it was essential. I'm sure you all know that, because this was a multi-person project. Okay, what does it do? The auditory image model uses a filter bank to do a spectral analysis the way your cochlea does a spectral analysis. So over here, let's see, do we have a, yeah, maybe we do. These auditory filters focus on one particular frequency and tell you what output is coming out of the sound at that frequency. There are 75 of these channels across the auditory range from about 100 hertz to 6,000 hertz, which covers the speech range. In this image, oh, and by the way, this is a 32 millisecond window. So in this image, when I say the vowel ah, I produce about 120 glottal pulses per second, which strike my vocal cords, strike my vocal tract. And each of those pulses strikes all of the filters, and they ring for each pulse. And at some frequencies, there are concentrations of energy, and at others there are not. These are the resonances of the vocal tract as they appear in the auditory system, and they are the formants of speech. And as those formants move up and down, so the vowels change. So I, O, that is a change of where the positions of those resonances are. Okay, the second stage of the model simulates neural transduction in the auditory system, and this pattern that comes out of that neural transduction is like the pattern of neural firing that is flowing up the auditory nerve to the brainstem. Okay, and you can see that the glottal pulses are still cleanly represented, and the formants are still cleanly represented. All right, now, this representation, which is like a spectrographic representation, it's time versus frequency, cannot be made real time. There are 125 of these cycles going past in my voice. For a child's voice, there will be 250. If you make this screen run past at that rate, all you will see is a blur. And there's just no way to solve the problem of wanting to look at this representation in this detail and have it be real time. You want to look at it in this detail because some of these features like this little feature down in here, is something that you hear. But if you averaged across in time and made a spectral profile, this feature wouldn't affect anything. You just wouldn't be able to see it. Okay, and its presence or absence wouldn't matter, but it's part of what you hear. All right, so this prompted us to realize that the auditory system must do something else, and what we think it does is it goes in and finds these larger peaks, and from each of these larger peaks, it calculates the times to the smaller peaks. So it uses a time interval code rather than a time code. So you just find those peaks, calculate the times to the related to nearby peaks, and you make one interval histogram for each channel of your filter bank. So you just take the timing information in the channel, make an interval histogram. That converts this picture into this picture, and now the abscissa is time interval rather than time, and this is a frame of a video. Time now runs the way we experience time in a video. All right. So in this representation, you can see that the glottal pulses have been aligned, and what you see is that all of these channels have a predominant interval at 8 milliseconds, which happens to be the period of the sound. So this ridge tells you immediately what the pitch of the sound is. The formants are now stabilized because they repeat, and so in the time interval profile, they stand up as features. All right, now let me show you what the video looks like. I'm going to show you one about pitch and one about timbre, for which I will use QuickTime. Whoop. Sorry. QuickTime does this. No, stay there. So the point is that in this representation of sound, which we think is like the representation in the head, things change in the video when you hear change in the sound. And when you don't hear a change in the sound, you don't see a change in the video. So this representation is a lot more like what you hear than any spectrographic representation. Let's see if we're ready. Okay, so this is the pitch ridge, and when the pitch is rising in the sound, you see this ridge moving over and all the others. And when you hear the notes as stable in the course of this arpeggio, the image is stable. And you're looking at very fine resolution.
You don't actually see the whole video.
Ah. Thank you very much. Once more. All right, and
Leo.
all right, this is the word Leo. I use it because the second formant starts very low in the O, it rises very high in the E and bangs into the third formant, and then in the O it comes back into the middle. So that's what you're looking for.
Leo. Leo.
Oh, I missed it. Well, so the point is that
Leo.
I did it twice. So the point is that you're seeing the formants move in that image up and down at the same rate that you hear them changing in the sound. Now in these demonstrations, we slow all the sound down because the visual system hasn't learned how to read these images, and the auditory system is very fast, but you get the idea. Okay, that's what it does. So we can make videos that express the dynamics that you hear in sound with the resolution that the auditory system has. All right. Okay, so what did this mean in terms of software? Well, we had to have a platform in which it would take in a sound and do all the handling of sound files. It had to produce basilar membrane motion, for which John Holdsworth produced a gamma tone filter bank. It had to produce the neural transduction module, which is adaptive thresholding and sharpening and compression. And then it had to use this strobe temporal integration to produce a stabilized auditory image, which is what we call this representation of sound, and it had to make the videos. In the late 80s and early 1990s, that was quite a lot. So I had these three people whose names I should have mentioned at the start: John Holdsworth, Mike Allerhand, and Paul Mason. To control the software and provide an interface to the user, we had an options handler written by Paul Mason. And it was a command line parser based on an options table, because this is how we understood, well, this is how we knew people would be using this program. So the options handler and the command line program looked like this. At the top there, you can see the command is genBMM. All of the commands had the form of generate something and then a three-letter code for what they produced. If you knew you wanted to start by producing basilar membrane motion, you type genBMM. If you didn't know what to do, you just type help and pipe it into more in the way you had been taught to in Unix, at which point this table would come up. It gives you a list of the options that you can control. It tells you what they mean, what that parameter does, and it tells you what the default value will be if you do not specify a value. Okay? So, here's one of the first commands that I put in because I'd been dying to do it for years. I wanted to look at the activity of a pulse train in the low frequency resolved channels. So I put genBMM. I want the minimum center frequency to be 220 hertz, the maximum to be 660 hertz, so this is emphasis on the low frequencies, and I want 15 filters per erb, which is a very high density of filters, and I want to do it on a pulse train, and I got this. So this, and the reason I wanted to do this was because I knew that for this in the auditory system, at the second harmonic, it must be going up and down twice per second, and that the motion would be essentially sinusoidal. But at the third harmonic of the fundamental, it would be going up and down 3 times. And at the fourth, it would be going up and down 4 times, and the fifth, it would be going up and down 5 times. But the membrane is continuous. So I wanted to know, how does this continuous membrane change the form? What is the change in the form of the motion as you go from one harmonic to the next, which was something I could not visualize, and I wanted the program to show me. And of course what you get is these elaborate saddle structures and some abrupt phase changes which you don't see at low frequencies. So I was very pleased with this, but that's just an example of what you do. Okay. So after you've typed help, you've learned to use some of the parameters. If you then want to store those parameters because you're using them all the time, you just say update, and the system made a file that it put in your directory to keep the parameters for which you had provided local values. So then if you typed help again, you would just get the parameters that you were currently working on, and there would be the default column of parameter values, and there would be the column of the values that you were currently using. Well, this immediately makes for a lab notebook mode of operation. When you leave and come back the next day, you know exactly what you were doing and where you left it and what the values were for the pictures that you might have printed. That all worked very nicely. So, fine, good. Okay. So, we had the option handlers. I was the manager. So I had a product, an auditory image, which my clients understood and which they were willing to pay for. But the auditory image also told the developers of the code what it is we needed to do. So we had a clear definition of what success would be in the project. The options handler captured the operation of the person. The remaining problem was that much of this was written in the middle of the night, and they would report to me that they had done something or fixed something, and I'd come in the morning, and first test I did on it, it didn't work. So we eventually realized there should be a test script, or I realized there should be a test script, and I told them to write it, but they never did. So I wrote it and said, okay, now when you finish, just run this before you report to me that it works. Well, they never did. This is absolutely beyond the people that are in a project of this sort. So in fact, the test script has to be written by the manager. It defines the project, and it's the manager that has to run it. And slowly, the other developers will learn that that's the first thing the manager is going to do. So maybe, I don't think they ever did run it. The other great thing about the test script is you can distribute it with the software, and the person, when they install it, you say, just run this script. If you get these pictures, which you can pick up off our website, then you know you've got the right project. Documentation, I'll leave out. We actually did it with a separate project, and that's what I would recommend. So, provide a clear development goal for the personnel and an interesting challenge. Provide a definite deliverable for the client with obvious milestones, and provide a means of specifying at any time where you are in the process and what remains to be done. That's another use of the test script. And that's what we did. It was great fun, and I can see from this morning's talks that we were learning some of the things that are now codified and described in courses. Thank you. I just want to say AIM did not survive the transition to Linux. It came forward in the form of AIM-MAT, a MATLAB version in AIM-C, and that's what Tom's going to talk about.
Okay, thanks very much, Roy. Time for a couple of quick questions. Okay, I just wanted to check Roy, you said it didn't survive the transition to Linux, so when did that transition happen for you? People stopped using Unix workstations about 2000, and by 2003 everybody expected to have this on Linux. Right. And we made some efforts, but we'd moved on to MATLAB, so and that was all the effort we had. Okay. Well, let's thank Roy. Okay, thank you very much.